Tensorflow with Keras is a powerful framework for developing machine learning models. Join me today as we learn the core features of this tool and begin exploring image classification. Welcome, I'm Gregory Tarfman with GNT Learning, and on this episode we're going to use Tensorflow to build some basic models. Now, Tensorflow is a rich toolbox to build deep neural network models suitable for everything from small, creative approaches to local datasets to massive distributed solutions using giant, state-of-the-art models. Today we're going to focus on the small end and understanding how these components fit together. This is a lesson for the true TensorFlow novice, and we're going to spend our time demonstrating the most common errors that occur so you can understand and use this tool effectively. With that in mind, let's go build some models. We're going to start off with an empty Jupyter notebook and bring in the imports for our usual numpy and matplotlib. Additionally, we need to import TensorFlow as TF, and we're going to import a piece of Keras as shown here. Now, before we get into the code, we need to take a moment to understand what is going on with TensorFlow versus Keras, and it's going to be important at the import level. TensorFlow is an end-to-end tool that allows you to do these mathematical calculations, and it really is a pretty general tool, but it was designed to be very efficient at running the kind of calculations and kind of operations needed for backpropagation and machine learning in general. However, TensorFlow didn't always have the best interface for use. So what came along was a tool called Keras that really acted as a wrapper for TensorFlow and a few other backends and allowed you to more efficiently put together and more easily put together a machine learning model and train it. So it was often historically much easier to use Keras than it was to use TensorFlow. Starting with TensorFlow 2.0, TensorFlow inherently supports internally the Keras interface. This means that instead of having to import Keras and use Keras to do the work with TensorFlow, you can actually just import TensorFlow, and then if you need access to some sort of Keras functionality, you can use Keras from inside of TensorFlow and import and use whatever piece you need. Now, this is important if you go back and use somebody's older code, is you might see somebody importing Keras directly and using Keras, and you might see people trying to import both Keras and TensorFlow and you're mixing the two. This is a little bit of a risky thing. If you get into more nuanced work, even just a little bit more nuanced work, you can run into some really strange errors when you have both TensorFlow imported directly and Keras trying to import and run TensorFlow itself. And these things don't always mix nicely. So it's really strongly recommended that you always just use TensorFlow directly and then use .keras from within TensorFlow if you want Keras functionality. That said, if you have some older code that's importing both or importing just Keras, go ahead and work with that code. It doesn't need to be changed. It can work. If it's working fine, it's working fine. The challenge is that if you're developing something new, it's going to be much safer, much less error prone to always import TensorFlow and use Keras from it rather than import Keras directly. That said, we can now look at turning our attention to some actual data. Today, we're going to tackle the image classification using the MNIST handwritten number dataset. Now, this is a very ubiquitous dataset that's been around for quite a while and very heavily used. You've likely seen it. It's the one where you have some handwritten digits and you're trying to understand, is it a 3, is it a 2, what is it, just from the picture. Now, because it is so ubiquitous, there's about 100 different ways you could come and import the data into your environment. This is just the one I'm choosing here, and I'm choosing it really for two reasons. One, it's showing that inside of TensorFlow.Keras, there's a lot of different little functionalities and tools available, such as loading this very standard dataset. Secondly, this particular way of loading it gives us the data as a simple numpy objects. There's a lot of different wrappers for different types of tools, your PyTorches, your Kerases, your TensorFlows, that will import it as some other specific type. In this case, we're just going to do the simplest thing and get our data in the lowest kind of denominator form, which is just a numpy array. Anyone who's ever worked with image data at all should probably recognize that you almost always have to normalize the data first. So we're going to go ahead and do that here by dividing both the xtrain and the xtest by 255. And this is just a sort of standard scaling that comes up because the integer way of representing numbers in memory is to put them on a 0 to 255 scale. But for doing machine learning work, we want to do it on a 0 to 1 scale in a float representation. So we just do a little bit of division here. Before we can actually build a model, it's helpful to understand what our data actually looks like and the shapes of what's going on. So we're going to go ahead and just do a little bit of simple prints here to see what our data looks like. And for anyone who's looked at the MNIST dataset or image datasets in general before, you'll recognize that this is going to be a somewhat futile process. All right, we look down here, we see that xtrain is this gigantic numpy array of a lot of zeros in it. But at a glance, looking at the data this way, we have just no idea what is going on with the xtrain. In fact, you could be a little worried if you saw this initially that, oh, is my data all zeros? Am I missing information? So we need to figure out how to actually look at these images as images. The first step actually is to just look at the shape of the objects to help us understand how this data is structured. So if we do that, we see we have 60,000 data points that are representing these 28 by 28 pixel arrays for images, and the wide train is just a simple one-dimensional array of 60,000 values for the labels. To actually see what is going on, we're going to use plt.imshow to visualize a single one of these images. And here you'll note that because this is a 3D object and we do open square bracket, 0, close square bracket, we're just grabbing the first thing out of this list of 60,000. What we're going to get is a two-dimensional object of size 28 by 28. And we're going to go ahead and use the CMap argument to make this a nice grayscale image as opposed to some sort of colored heat map. And as you see, what we have is this sort of pixelated, crudely drawn 5. Alright, so now that we've gotten the basic idea of what this MNIST dataset is out of the way, let's start building a model. So, Tensorflow is a powerful tool. Let's start off with the simplest model we can make, which is probably a multinomial logistic regression. Now, multinomial logistic regression is really just a very fancy way of saying we're going to do a linear transformation to the data and then apply a softmax to convert the evidence into probabilities. To do that, we're going to use the simplest form of building a model here, which is keras.models.sequential. As the name implies, you're building a model that is sequential. In this case, it is sequential in the sense that it can have multiple layers in it that do different transformations, but simply the output of one layer is the input to the next layer, and so on and so forth sequentially. Now for this very simple model, we actually only really need one layer, and we're going to use what's called a dense layer and give it a few important arguments. A dense layer is one where we're doing a fully connected or have a dense set of connections that is this full-blown linear transformation, takes all the values of the input and uses them in linear combination to get all the values for the output. This first number here denotes how many nodes are in the network in that sense, or simply the length the vector is producing. So we're going to have some image of pixels coming in, and we're going to have 10 values come out. Second part here, we can optionally define an activation, and that is almost always the case that you're going to have one. And here we're going to be using the activation of softmax and also work on our spelling of the word activation. And the softmax activation is convert our vector of 10 outputs into a vector of probabilities that will sum to 1. And we're using 10 here because there's 10 possible digits, 0 through 9, and the probabilities we're going to assign or try to determine are the probabilities that the digit written is a 5 or a 4 or a 3 or what have you. This formulation of having a vector of values going through a softmax as your final layer in a model is very standard for multi-class classification. And the last thing we need to add here is this input shape argument. This input shape argument tells the model how big the input's going to be, because as part of building the model itself, it's going to have to create some internal coefficients, and it needs to know how big those coefficients are going to be based on the size of the objects coming in. The shape we're going to use here is xtrain.shape1:. Now, we're going to come back to why this 1: is here in a minute, and we get a little bit more detail about how shapes work or handled within the Keras interface. Holding on to that detail for a moment though, we've now defined a complete model, save for a few little typos we need to correct. Make sure everything is good. And we now have defined a model, technically speaking. Now, as you can see, this model object itself is some complicated piece of architecture. Now, we can go ahead and save this to a variable name, use it, run some things, but this isn't particularly in a useful form just yet. Technically, all we've done is define the operations. We haven't really built the model. At least I've not built it in the sense that we could use it for actually training and learning. To do that, we're going to have to add a few more pieces here. So first of all, let's give this thing a proper variable name so we can refer back to it. Second, we're going to go ahead and learn how to compile the model using .compile. And what this .compile does is basically set up the options so that when we do training, it knows how to go about doing the training. This means defining the optimizer it's going to use. In this case, we're just going to use the Atom optimizer. It should be a good default choice. And we're going to define a loss. In this case, we're going to use categorical cross entropy. And categorical cross entropy is generally the loss you want to be using for multi-class classifications. Now, lastly, we then take the model.lr and do a .summary. And we get a nice little report of how the model actually looks. All right. So So we see here that we have this pretty simple little description of what's going on, that, okay, we have a single layer for a model, it has a dense layer, and it has this output shape. But why do we have an output shape of none 2810? What is that about? And we never did really explain what was going on with this 1, 0 for the input shape here. What's going on here, the first thing that comes up is this none. What is that about? And it really corresponds to the same thing that's happening here with this 1 colon. When Keras or Keras-based objects talk about shape, what they're really talking about is the shape excluding the batch size. Our data has 60,000 points, but not all 60,000 points are going to go through the model at the same time. It's going to go through the model in batches. And that batch size might change as we change what we're doing in our hyperparameter optimization and messing around with things. And so the model itself actually doesn't care what the batch size is before you do any runs. And so we have a none placeholder here being used to say, yeah, there's going to be some number of data points come in, and they're going to have some shape, and we're going to do some stuff with them. So the input shape, it doesn't really care how many points it's going to get at a time. It just needs to know what's going on per point. And so it was interested in our initial 28 by 28 for our image size and didn't care about the 60,000. Hence why we have this 1 colon at the end. And hence, when we talk about output shapes and all the various layers, you're always going to see this none in the front. Because this none corresponds to the batch size, which isn't really important to that model definition itself. Great. So that explains the none. So why do we have both a 28 and a 10 here? Well, what's going on here is our input was a 3-dimensional object. If we go back and look at xtrain for a moment, we'll recall that it was 60,000 by 28 by 28. It wasn't a 2D object. The way the dense model is defined is it acts on the last layer of an n-dimensional object. If we're wanting to act on all the pixels and use all the pixels independently to be part of the determination for what the outputs are, we need to flatten this into a 2-dimensional object first. We don't want this image to have the structure of an image if we're just going to do something as simple as apply a dense layer over top of all of it. Now, note that having the dense layer only operate on the last layer and simply loop over other layers actually provides some interesting functionality for more complicated systems. In older versions of TensorFlow, there was a concept of a time-distributed layer. It turns out that just the basic dense layer now covers that functionality as well. We won't be going into some of those details today, but be aware that this is actually a very nice feature for working with more complicated systems. In our case, though, we're building the simplest model possible where we don't really want to understand the concept of the image having a width and a height. We just want to have raw pixel values and put them in. So to that end, we're going to come back to our model, and we're going to go ahead and flatten the inputs before we get them. To do that, we simply add in a new layer called .flatten. And the .flatten layer, as the name suggests, will flatten the inputs. And it'll take a n-dimensional object and reduce it to 2 dimensions, one for the batch size and one for all the information. Now, you can see here this kind of generalizes our use of sequential. We can just make a list of layers to build our model. We also see that this input shape has to move, because now the dense layer is no longer the input layer, and we can move this little label up. A little bit more elegant solution that becomes useful when we get into some more complicated syntax is to actually use an input layer specifically that defines what's going on here. So we're going to say layers.input, and we're simply going to give it this shape here and remove this shape here. So what this is doing now is saying that, okay, the model is being told a priori that it's going to get an input, it's going to have this shape, and then it can figure out everything else from there. When you have multiple layers in a sequential model, the layers talk to each other enough when they're being built that they understand that this guy can figure out what his input is from this guy and can figure out what his output shape is going to be and tell the next layer. The next layer can use that as its input shape, etc., etc. And now, when we go ahead and run this, we realize we need to put a comma here because this is a list. We are able to see we have a 2-layer model. The input doesn't really show up. And in the first layer, we flatten our input. So we now have a none by 784 object, where 784 is 28 times 28. So we flatten the image. And then it goes to the dense layer, which then converts that 784 values through a linear transformation softmax activation into 10 output values. And one little detail here, just I left off that was not critical, is you can also define in this compile a metrics. In this case, we're going to define accuracy as a metric. And there are other metrics available, precision, recall, etc., etc. We'll go ahead and run that. If you've been paying especially careful attention to shapes and what's going on, you may already foresee an issue, but just hold on to that thought for a moment. And let's pretend everything looks perfectly fine. And we decide we now have a model, we have some data, let's go ahead and train it. Model lr.fit, give it our training data, give it our testing data, and something is amiss. What happened? Well, this is going to be one of a pretty common set of errors that you'll run into when you're first using TensorFlow. And if you scroll all the way to the bottom, it usually gives you a pretty good idea what's happening. So it's complaining about shape 32 by 1 and 32 by 10 are incompatible. Without reading through all the detail of the code, we can actually pretty much know what this means immediately. So there's 32, okay, question mark what that means, 1, and 10. Well, 10 should be pretty obvious where the 10 is coming from. It's right there. So what we're looking at here actually is an issue with the output itself. And the 32, after a little bit of head scratching, you may realize that we are doing this in batches. The default batch size is 32. We didn't specify a batch size anywhere, so we're using a batch size of 32. So it's saying that it's trying to compare some batch with 10 outputs to some batch with 1 output. So where did the 1 come from? Well, this may require a little investigation on your part to figure out, but if you have a very good memory, you remember that back here, that our y values, there weren't 10 values. There was 1 value. It was either 3 or 4. It wasn't a probability of a 3 or 4 or 5. It was simply a 3 or 4 or a 5. So there's only 1 value associated there. So how do we deal with that here? And really there are 2 options available. The first option is the kind of simplest one you'll see a lot, which is, well, let's just convert our data to the same form as the model to make it work. So we can make a y1hot representation where we take and use one of the helper functions from TensorFlow, in this case tf.1hot, and convert our training data into a 1-hot representation with 10 values. So this will just look through the list of 3, 4, 5. It'll convert 4 to a vector of 10 zeros with a 1, i.e. 1-hot, in the 4th position. And using this, we could, in theory, run the model. Now, this is the solution, but we're going to actually end up with a very interesting little secondary error when we run this. So I'll tell you right now that this code, as is, runs perfectly fine. But we got an error from a kind of unique source that does come up time to time with TensorFlow. And without going into the details here, what we basically see is that we have a complaint about this first call to a function and something not lining up. What happened here is that when we call model.fit, it tries to figure out how to build the model and set some things up at the very last minute. Not when we did the compile part earlier, but at the very last minute we're doing the fit. Because we had a misshapen y data initially, it used that to finish doing some setup. And that setup is carried over to the fact that even though we fixed the data now, it's still trying to use this wrong previous setup. And this is what this non-first call is about. That something is inconsistent between what it did the first time it was called and what it's doing now. And the real solution to this is actually to restart and rerun your kernel. So I'm going to go ahead and restart and run all. And this will take a little bit of a moment to run and what have you. And without too much ado, we now see we have a running model. So by switching to a 1-hot representation, we made the input data match or the actual shape of our model itself, and everything can run. Now, that specific error we just saw where there was a mismatch and it wasn't working right, we had to restart and run all and everything worked fine, that particular error is not an especially common one. But there is a whole lot of errors like that can occur, especially when you're reshaping and rebuilding models, that a lot of times simply restarting and running all can fix some of these very strangely worded, weird-looking errors. So, as a general rule, after you fix shape errors, if you still have a strange error going on with a very long-winded error message, simply try a kernel restart and run all, and that'll often fix the problem. So this was one solution to making our data fit the model. The other solution is to make the model fit the data. Or perhaps more accurately, I should say what we're going to do is instead change the way the model trains to fit the data. So let's take our model right here. We're just going to leave this up here as an example for how to do this with a one-hot representation. And we're going to make a new model. And we're not going to use categorical cross entropy. Instead, we're going to use sparse categorical cross entropy. Now, this is a little bit of an unusual formulation in some sense because the model looks completely identical because the actual architecture of the model itself is the same. But during training, instead of using the vectors in a one-to-one way and saying, oh, okay, I have a vector of 10, I got to compare it to the y vector, which is only of size 1, there's a problem, it takes this vector of 10 and compares it to sort of an internally automatically one-hotted version of the y. So now we can actually go ahead and do our training directly on the original data as is without doing the one-hot transformation. Now, this is important too to notice that this is actually a pretty helpful behavior because this sparse representation allows you to write a very small version of your y data as opposed to a very large, expanded, dense version. Realistically, it's usually not going to be an actual problem, but it is just a little bit nicer in general to use this sparser representation when possible. All right, so we let that run for just a moment, and we see we have some sort of result here. So what's going on? Well, we see that we've run the model for a while, and this was automatically moving when it was running, and we have some sort of estimation for loss and accuracy on the training set we're running on. Now, there's an important detail to notice here. If I take this cell and I just run this same thing again down here, you'll notice that again it starts to run. But if you look at the loss value that we got for the previous run, it got down to about 0.47, actually about 87%. But I ran this again and it's getting better. And that's because when you do this .fit, the model is being updated. And the update isn't some just one-time result for the current estimation. It is a permanent change to the variables in the model. And so running the cell again, or copying and pasting it so it's more visible in this case, we actually continue the training from where we left off. If you wanted to actually restart the training, you need to go up to where the model is defined and redefine a new version of the model, or by some other more involved means, change and reset the coefficients. So now if we go ahead and rerun the model down here, we'll see starting from scratch, we should get something that will converge to about the same value it had up here. Now the next thing we need to do is explore a little bit more of the options available during this fit process. So while it's running, I'm going to go ahead and do some writing on this code itself. The first option we're interested in is the number of epochs. So in this case, it ran for one epoch, which is noted by having one line here. And an epoch means going through all the data once. Maybe you want to go through the data multiple times instead of just running the same cell 10 times. A second option that's very handy is batch size. Batch size, we said before, has a default of 32, but sometimes you want to run more or less batches at a time. This has some various trade-offs, which will be up to you to figure out how you want to handle that. And the last one I want to mention here is the validation split. Now, there's a lot of ways of giving validation data to this. What the validation split does is it says take 20% of the data at random and use it for validation purposes. All right, let's go ahead and start this running. What this means then is that from the training set, you're taking 20% of the data and holding it to the side as part of your calculation. So now, as this thing runs, we'll see, first of all, we have multiple epochs. We'll also see that in addition to having the loss and the accuracy being displayed for the training set, it's also outputting a validation loss and validation accuracy on the validation set. Initially, these values will be pretty close together. If you run the model for long enough, the training set will continue to improve, and the validation set will eventually stop improving. There is an important caveat here about doing this validation split and reruns. Just as we showed that we could have the model pick up where it left off by running the cell again or making a copy of it and running it, the one thing to be aware of is that the validation split is going to be a new random split. So if I rerun this, I look like I pick up where I left off, but I'm not actually doing the same thing because I'm going to have a different validation split, and so the model will see different data. This can lead to misprediction of the validation errors. So if you do want to do a validation split like this, you need to make sure you do all your epochs in a single run. You can't do multiple runs and aggregate the data. And the other way to provide data for validation is instead of using this validation split, we can go ahead and use a second option here called validation data, where we just directly say, oh, use x test and y test. And we could run this from here. And then this simply would use the preset data we've prepared before for x test and y test and evaluate on them instead of a random subset of the training set for validation. There are a lot of important details in design of experiments about how you do your validation and test split, which are going to be beyond the scope of our discussion today. Today I just want to point out that you can use validation data in order to take an externally pre-prepared data set and see how you're doing on it. And you can use validation split to take a subset at random from your training set defined here. All right. So with that, we now need to kind of discuss how we're going to keep track of all this stuff in a little bit cleaner of a fashion. Because, this is a very handy data table when it's running to see what's going on, but this isn't particularly presentable. So one thing we can do instead here is we can turn off this long-winded data table using verbose equals false, and instead save the results of our model fitting to another variable. I'll go ahead and comment out this for the moment. And we're going to restart and run all, because now we want to refresh the model from scratch and go ahead and let it learn and save the data in this history. So while we do that, we'll go ahead and use the magic of editing and skip ahead a little bit. All right, so once that's run, you see we don't get a long verbose chunk of text to screen, and instead we have this history LR. Now, this history LR itself is a little bit more complicated than we're going to get into today, but the main thing of interest for us is that this history LR has a .history in it that is basically just a dictionary of the results we were looking at on screen a moment ago. With a little effort here, you can do some plotting. Let's go ahead and paste that in. And we can turn this into something that's a little more visually appealing, both for our own internal understanding and for sharing and showing others as well. And we can see how the training and validation, loss and accuracy are changing during the course of training. Now, so we can see overall that the accuracy of our model is around 92%, which for the MNIST model is what you expect for a pretty dumb model to be able to achieve without any particular sophistication. Let's say we want to evaluate this on some external data set, once again, that wasn't part of our training itself. Well, there's a couple options available to us. The first one is we can take our model that we've used and we can use .evaluate to look at some external data. In this case, this is exactly the data that's being plotted in the validation line above. And when we run this, we get a little one-time run through all the data, and it will tell us what the final loss and accuracy on that set was. And if you look very carefully, you should see that this 0.267 should match the orange here, and the 0.926 or 927 really matches what's going on here. So that's a great way to test your data set. The next thing you might have is the case where, all right, I don't have a y value, I just need to see what my predictions are. So we can do model LR.predict, and we can give it a set of data to look at. Now, I don't want to see the predictions for every single one of these 10,000 values, so I'm going to go ahead and just use :5 here, so they only give it the first 5 images in the training set, or rather the test set, and see what kind of predictions it's making for those. And it also helps to fix your typos. And what this .predict is going to give us is the raw results from the model. Now, as you recall, our model was outputting vectors of size 10 for each image. And so that's exactly what this vector is. During training, it understood by using the sparse categorical cross entropy how to relate this back to comparison to a label of it's supposed to be a 5 or a 3 or what have you. But the value it's going to give us in the predictions is a little bit more raw. Now, this is actually a good thing in a lot of circumstances because sometimes you don't want to just know what the prediction is, you want to know how confident it is. And if you look at these values carefully for a moment, you'll see that the maximum value here is this 99.4% or 0.994, meaning that it thinks that this image has a 99.4% chance, or really rounding to 0.5% chance, of being this value. Now, obviously, this is not the easiest thing to interpret directly, so we're going to do a little bit of code around this. Let's go ahead and call this value here the probs, and we'll go ahead and make some predictions, which will be the np.argmax of those values along axis equals 1. As always, for NP arguments that do aggregation, either maxes or what have you, the axis you're defining is the one that's going to go away. We want the first axis, which is these 10 values, to be reduced to a single value, and argmax gives us the index. And then just for readability here, we'll say for I in range 3. Let's print not only what the probabilities are for that particular one, and let's do a little nicety here and make this something that we can then have as a understandable report. We're going to then do plt.imshow of the image itself. And this is just directly the same as the code we had above, where we were pulling in, looking at the original CMAP gray version of an image to make sure we can understand what the data looked like. Raise plt.show. And provided we don't have any typos, we are going to have a nice little summary here. It says this is the probabilities for the image, which means that the prediction is 7, and here's the image in question. And we're doing this case for the first 5 images, and we can see the model is doing relatively well. Rather, I'm doing the first 3 images here. Just going to change that to 5, just to give us a little bit more stuff to look at. And we can see the model is doing relatively well. And, for example, this one is a little bit of a harder one. In my mind, I could see that could be a 6, but it was pretty confident. Now, this is a nice little way to kind of demonstrate what's going on, but it's also something where I see a very, very common error, which is someone trying to use this on a single value and having an issue. Here, you notice I took the first 5, and it worked just fine. But if I take this little snippet of code, and I run it down here, and I say, well, give me the predictions, or rather the probabilities for image number 18, I'm going to get an error. And the reason for this is shape. And it's going to really not be super comprehensible reading the error message itself, but the evidence is there. It's saying it's looking for something with 784 values, but got 28. What happened here is that the model was given something that was a 28 by 28 array. It assumed that the first 28 was the batch size, and so after the flatten operation, it created a none 28 object. But the next layer in the model was looking for a 784 object, and so it didn't line up. What the underlying problem here really is that before, when I was doing xtest:5, is I was given a 3-dimensional object that was 5 by 28 by 28. This is 28 by 28. What I need to give it is a 1 by 28 by 28. I need to have a first dimension there that is of size 1, because there's only one image. And by default, we're going to reduce the dimensionality. So there's really 2 solutions available here. One is to reshape this to the right shape and run it, and it'll be able to give us our values. The other one that's a little bit shorter in syntax, but probably not as easily understood, is to just make sure to do an actual slice rather than do a simple grab of a single value. And this will work either way. Really, it's going to be kind of more a matter of personal preference, but the key to recognize is that this predict is expecting something that has multiple images or multiple inputs, and so you need to give it something of the correct shape. Great. So now that we have demonstrated how to build a model and how to get results from it, evaluate what's going on, that's great for a simple model, but now I want to do something more complicated. That was a cute little 1-layer model. What if I want to do something more involved? What if I want to build something a little more serious? Well, it turns out that doesn't really get much more complicated in terms of syntax. So let's go back up to the model we had here. We had a nice model right here. We defined this sequential model, did a few options. Well, let's say I want to do some sort of multi-layer perceptron next. Right? And come on down here, and we're going to find ourselves a MLP model, MLP, multi-layer perceptron. Okay, well, first of all, we should change the variable name so we don't have any confusion later on. It's always a very good idea. And now we're going to add some additional layers here. So additional layers we're going to add are going to be some additional dense layers to make it a multi-layer perceptron. So we're adding 2 hidden layers. And the difference here is we're going to give these internal layers some hidden dimension, so 64 in this case. And we're going to change the activation from softmax, which would be kind of a strange activation function for anything but the final layer, to ELU. Now, ELU is much like ReLU, if you're more familiar with that. It's just a mathematically smooth version of it. Ultimately though, it's kind of immaterial what the exact activation function is. It's something you can play with and try out, but any real activation function that is defined part of TensorFlow could be used here, which is going to be most of the common ones. So with this, we've made some very minor changes, and now we've defined a completely new model. And that structure is reflected in this dot summary. So now we see there's multiple layers. After we flatten it, we have 2 hidden layers with being created. And we also see the number of coefficients in the model went up drastically. So now we have 55,000 coefficients to be trained, as opposed to our original set of 7,000. So this model is on the order of 7 or 8 times more complicated in terms of what it could possibly fit. We're also going to go on up here, and while we're copying and pasting things, we should go ahead and copy and paste the way we did our model training. And we can use that exact syntax as before to see how the model is going to do down here. Let's call this history MLP. We'll change it to the MLP model and let that start to run. And really no additional work is required on our side other than adding 2 layers to the model, and we now have a more complicated model, and we can see how it does. Now up to this point, you've probably been in the habit of running one cell in Jupyter Notebooks and waiting for it to finish. This cell can take a while to run. There's nothing wrong with adding another cell and going ahead and telling it to run. It'll automatically pick up and run when the previous cell finishes. And after a little bit of waiting, our MLP model finishes, and we can look at the results, and at a glance we can see it actually is doing a fair bit better. We can see that the training accuracy at the end is up over 98%. For the validation set, or really our test set, matter of labeling here, is about 97%. So this model is doing better than our more simplistic model we had a moment ago. We can also begin to see more complicated and nuanced behavior. There's actually a gap here between training and validation set, meaning the model is starting to have a little bit of overfitting going on, and we can start to investigate methods for changing that. One other thing that comes up here is I set a lot of arbitrary coefficients here. I said 64. I put 2 dense layers. I used ELU. These were all very arbitrary decisions and not tested at all to determine that they were the best possible ones. I maybe knew from previous experience that these are reasonable values and reasonable choices, but there's no reason to think these were the optimal set of choices. So you might want to play with and tune these values. But as you can see, this starts to turn into kind of a lengthy notebook. I have a result up here with some model, I have some plots, I have some values and things I'm evaluating, then I made another model, more plots, and you can see how this very quickly becomes an unwieldy, long, crazy thing to look at. So another topic for a future video is going to be organizing this hyperparameter optimization search and managing these kind of ridiculous amounts of data you begin to generate as you evaluate different models. Thanks for watching, and a special thanks to those whose contributions help fund and sustain creating content like this. As always, the code produced today is available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.